Hello, wonderful calculus students. Today we are going to learn about a new method for finding the antiderivatives of more complex functions. So the rules that we have so far won't work for these new functions, and that's why we're learning this new method called U-Substitution. So just to kind of back up and kind of review why we need this method, when we learned to take derivatives, one of our rules was the chain rule. So for example, a problem like this would require the chain rule. Since it's not just e to the x, we actually have a function in that exponent, we know we need the chain rule. And so what the chain rule said is start with the very outside function. So in this, right, our function was kind of this exponential. So I know the derivative of e to the x is just e to the x. So we just start by taking e to the sine of x. But then we said now we actually need to take the derivative of this function that's in the exponent. And so since the derivative of sine of x is cosine of x, we had to multiply by cosine of x. So our derivative was e to the sine x times cosine of x. So since we're working on finding antiderivatives that we can use to compute areas, we need a method that undoes this chain rule. And so we call that method U-Substitution. So we're going to go through a problem step by step here, and then we'll do maybe one other one in the video. So here's the big idea, right? We have to get rid of the chain, that extra piece that comes from the chain rule. And here's how you'll know you need to use U-Substitution. If I look at this function, sine of x times e to the cosine of x, there's no function I know that has that derivative. So it's not just a straightforward one that I could have memorized. So that tells me there's something here that came from the chain rule that I have to undo. So here's how this is going to work. Our first step is to choose a u. Right? And when I say that, when we pick this, we choose a u based on, this is kind of the thing, this is whatever, I'm going to say caused the chain. So what thing in there is causing this extra piece to happen in the chain rule? So if I look at my function, sine of x actually isn't causing me a problem. We could do that without invoking chain rule. But now I see I have this e to the cosine x, right? That's something that I have to do a little something extra to deal with. So that piece here is going to be my u. So I just kind of write it off to the side here. I'm going to say my u is cosine of x. It's kind of that extra piece that goes with my exponential function there. So now, once I've got my u, I'm going to calculate du. Right? That just means to take the derivative. Right? Or find du dx, assuming we're in terms of x here. So I have my u, so I know the derivative of u with respect to x. Well, derivative of cosine is negative sine of x. Okay, so now we're going to do this next part in two pieces. The next thing it says to do is to solve for dx. So in other words, in this derivative here, I need to isolate the dx. So I'm going to do that. Most times you'll see I'll just do it in one step, but since this is the first time, we'll go through it in a couple steps. The first thing I'm going to do, I'm just going to recopy this to show what's going on here. That was my derivative. So I'm going to multiply both sides by dx, so that it cancels here, and I have du equals opposite sine of x times dx. So now if I want dx by itself, I'm just going to divide both sides by the opposite of sine of x. And now I have that dx is equal to du over opposite sine of x. All right. Now, the second part of that says to substitute. So here's what we do. I'm going to box this off because this was kind of all the prep work I needed to get going on this problem. So here's what I'm going to do. I'm going to copy the integral. Now, I'm not going to copy these bounds down right now. We'll deal with those in a little bit here. And here's what I'm going to do. In my integral, I notice I have sine of x. So I'm going to copy down the sine of x. Then I have my exponential function, but what I notice is that this cosine of x is just my u here. So instead of writing cosine of x, I'm going to substitute that u. Now, dx here, I know that dx is equal to this expression here, du over the opposite sine of x. So sine x I didn't have another value for, but I had other expressions for cosine of x and dx, so I substituted those. Now, here's what you should notice. If you've done this correctly, anything with an x in it should cancel at this point. So I see I have a sine x here and the opposite sine x here. So I could simplify this to the integral. I still have my negative. I have e to the u du. So now I have my function is in terms of u, I have a du, and I don't have any x terms left. If you have anything with an x in it at this point, you know you've done something wrong. Now I have to deal with these bounds. It was from 0 to pi, but that was when my function was in terms of x. Now that my function's in terms of u, I have to change those bounds. So here's what I'm going to do. Here's my new function u. So I'm going to look at my upper bound. I had u of pi. If I substitute pi into this equation, I get cosine of pi, right, which we know is just -1. Whoops. I don't know why I have that in parentheses. Cosine pi equals a -1. So now that upper bound that was pi becomes -1. So I'm going to do the same thing here. U of 0 is just cosine of 0, and that's equal to 1. So where my lower bound was 0, now for my new function, I have a lower bound of 1. Those are all the new steps for U-substitution. From here on out, you're just evaluating this integral using antiderivatives, just like we did in the previous lesson. So from here, this is a nice, easy problem now. We've boiled something down, or something that was really complicated, down to a really easy problem. I know the antiderivative of e to the u. It's just e to the u. I have my negative out front. I still have my plus c, so nothing has changed there. And I'm evaluating from 1 to -1. So I know that I'm going to have the opposite of e to the -1 plus c, and I'm subtracting the opposite of e to the 1 plus c. So I'm going to have negative e to the -1 plus c plus e to the first power minus c. My c's are going to cancel, and I get negative e to the -1 plus e for the value of my integral. So again, kind of these steps from here down haven't changed at all. It's all in the process of selecting the u and doing your substitutions. So I'm going to do 2 more problems so we can kind of see this process, and then we'll practice obviously a lot more with this tomorrow in class. So let's look at number 1. Make sure I've got this where you can see it. I'm sorry, I'm going to kind of box all this stuff from the previous problem. Kind of ran over there. Okay, so for number 1, if I'm trying to identify my u, the first thing I notice is 4x. That wouldn't cause any chains or anything to happen there. But here I have some quantity other than x which is being squared, and I know that would invoke chain rule. So that's what I'm going to identify as my u, is this piece in the brackets there in parentheses. So my u is going to be 2x squared plus 1. Okay, my second step was to find the derivative. So derivative of u with respect to x is going to be 4x. And then we solved for dx. Well, now I know if I multiply by dx and then divide by 4x on both sides, I'm going to get that dx is equal to du over 4x. And now I'm ready to start tackling this integral. Again, what I'm hoping to do is make this into something much easier to find the antiderivative of. So let's see how this one works. Now, this integral, as I start doing my substitutions, again, I'm not dealing with the bounds just yet. I'm going to kind of box this off here. On top, I have 4x, and I don't have a new variable for that, so that's going to stay 4x. On the bottom, this 2x squared plus 1, that was my u, and I still need to square that. And now my dx, I'm going to replace with du over 4x. And remember again, the idea here, if I've done it correctly, all my x terms should be gone. I should just be left with u's and a du. So luckily here, I see my 4x's are going to cancel. And I'm left with the integral of 1 over u squared du. And if it helps, we just can consider this as u to the negative 2 du. So now we're going to address the bounds here. So again, I need to change this. These were my bounds when my functions was in terms of x. Now we're going to do it in terms of u. So my upper bound, if I take u of 2, this is going to get plugged into my u equals. If I plug in 2, I get 4 times 2 is 8 plus 1 is 9. And then my lower bound is negative 1. So I have 2 times a negative 1 squared. That's 2 plus 1 is going to be equal to 3. So my new bounds in my problem are 3 and 9. And again, from here on out, it's the exact same process that you already know how to do. So I'm going to take my antiderivative. If I add 1 to this, I get u to the negative 1. I divide by a negative 1, which is going to make this a negative. I have my plus c, and I'm evaluating from 3 to 9. Now, I like to think of this instead of u to the negative 1, I have negative 1 over u plus c from 3 to 9. And so now I see I have negative 1/9 plus c minus a negative 1/3 plus c. If I simplify, I get negative 1/9 plus c plus, because I have minus a negative. Now I'm going to make a common denominator here, so 1/3 is going to be 3/9. If I distribute that negative, I have a minus c, so those are going to drop out, and I get negative 1/9 plus 3/9. Sorry, this is kind of jammed into the bottom here. It's going to give me a value of that integral of 2/9. All right, we'll do one more, and that will be plenty for right now. So we'll flip and do number 2. So while I'm getting situated here, look at number 2 and see if you can figure out what would have, well, still can't see that. What should our u be? Now, when I look at this problem, I notice that secant squared is actually the derivative of my tangent here. So I'm thinking my u is going to be my tangent of x, because then when I go to differentiate it, I have my derivative here, and that'll be a nice, easy substitution. So I'm going to make my u equal to the tangent of x. If I stick with my colors here now, my du dx is going to be secant squared of x. So I'm thinking this is going to work out pretty cleanly and nicely. And my next step, I'm going to solve for my dx, which is going to be du over secant squared of x. So I'm going to ignore the bounds for a minute. I'm going to get this set up. So I have the integral. Now, my tangent of x here was just my u. So instead of putting tangent of x, I'm going to put u. I don't have any variable defined for secant squared of x, so that's going to stay. And then my dx is going to become this expression here. So instead of dx, I'm going to put du over secant squared of x. Oops, sorry, this is crooked. So now, again, I'm happy here. I notice these secant squared of x terms drop out. So all I'm left with is something really easy to deal with. It's just u du. And all I have to figure out is the change of bounds now. So I'm going to take u of pi over 3. So that's asking for the tangent of pi over 3, which is just going to be square root of 3. Then I'm going to have the tangent, u of 0, which is tangent of 0, which is just going to give me 0. So my upper bound was pi over 3. That's going to change to root 3. My lower bound was 0, and that actually stays a 0 in this case. And now we do our normal process with antiderivatives. So I'm going to use power rule, becomes u squared over 2 plus c from 0 to square root of 3. So I have square root of 3 squared becomes 3 over 2 plus c minus, 0 squared over 2 is just 0 plus c. So my c's will cancel out, and then 3 halves minus 0 just leaves us with 3 halves. Okay, so for today we just wanted you to be kind of familiar with how this process works. Tomorrow when we're back in class, we'll do 2 examples together, either with just your small groups or as a class as needed, and then you'll get lots of practice working through these problems. All right, that's it. Have a great night, and I'll see you tomorrow.